Hey, Chris.
Hey.
How's it going? I just realized I started the broadcast a little too early. I was like talking with too many people and hit start broadcast, so I will just trim this out
Is that easy to do?
when I save it. How are you doing?
I'm great.
Interesting. So if anybody's joining us now, we're going to wait for David to join, and then I'll get into it.
Right on.
And perfect, David's here, so we can start right away. Hey, David.
Morning.
So we're going to get right into it. Today I'm going to be talking about how can.stache works. And can.stache is can.js's live binding template engine. David and Chris are here to provide play-by-play and color commentary. Meaning that you guys, when I'm being confusing, you should stop me and help me clarify whatever the points I'm making are. Or if there's other things that you know or are interested in about, please ask those questions and we'll talk about it. So let me share my screen and get going. So again, this is in a presentation. All right, can you see my screen?
Yep.
Sure can.
Good.
Awesome. Okay, so we're going to talk a little bit about why we made the switch to can.stache instead of mustache, an overview of what can.stache is, and then talk through a lot of the sub-utilities that, when you combine them all up, make can.stache. So why can.stache? Overview first. I don't know why that Y was there. Maybe that comes later. So basically, you use can.stache. You provide you call this can.stache method. There's a lot of different ways of getting a can.stache template. This is the most programmatic way. You call can.stache with a string that represents the content of your template. That creates what we call a renderer function. Which is a renderer function. A lot of times we'll just say it's a template. And then you can pass that template, you can call that template function, that renderer function, with data. It can be observable data. And that produces a document fragment. It renders the template and, produces a live document fragment. A document fragment is you can think of it as like it's like a container for elements that are not attached to the DOM. It's a container for elements, multiple. It's like a special form of an array for elements. The fragments are really nice because anything you can do with an element, you can pretty much do with a fragment. So you can call a pen child with a fragment.
But one of the advantages of the fragment is that it's not actually in the DOM yet, right? Like when you work with the DOM fragments, you can work with them outside of the actual DOM tree.
Yeah, they have to be. All the elements in a fragment have to be outside the DOM tree. So yes, that you can add things to a fragment without affecting the DOM, causing reflows, which is really nice for performance reasons. So you can also, because this is a live binding, if I were to add to my list of tasks, a new task, the live binding of the template would automatically create a new LI and insert the LI in the page.
So I think that's important to mention, right? That it only creates that LI and adds it. It doesn't re-render the whole section, the whole URL.
Let's see. Depends on how I wrote my template. Yes, because I used each and not just pound tasks, it will in fact do that. It will not update the whole document fragment or the whole UL, rewrite the insides of the whole UL again. We'll just create a new LI and add the LI. Good.
And that makes a really big performance difference.
Yeah.
Everybody should know.
So, and not only, well, in 2.3, it starts doing diffing too. but we're not going to get into that here. But even if you're not adding things to the same list, it can still figure out what's been changed between two different lists and only update when it needs to be updated. So what we are talking about today is about how to build this. And it's a tricky thing to build a live binding templating engine. The challenge, which you really need to do, is in some ways break down, given a template, you need to break it down into kind of sub-templates and then be able to convert those to fragments and wire up live binding, right? So we have to be able to say, like, oh, there's a UL element, and then, hey, there's this each subsection. And within that subsection, well, it creates LIs, but these LIs have different live binding parts. Sometimes live binding can be in a attribute. Sometimes it can be just in a text area. And this section might need to produce, multiple LIs, this each block, right? How do you make that happen? And then what eventually it needs to do is say, okay, well, what can.stache does is eventually it'll make the UL, and then it'll run the behavior for the each, which might create a bunch of LIs, and then it needs to go inside each LI, hook up the ID because that's special, and then go and hook up the ID attribute because that's live bound, and then it might have to go to the text nodes of the LI and update whatever the name is, right? So there's this whole cascade of changes that need to be kind of wired up correctly in can.stache. I didn't realize I was a believer. It's one of my hobbies here. So I'm not going to go through the steps to do it because I'm just going to get into it because I don't think that actually slide is useful. What we are going to start with is, in some ways, the piece of technology that, this is in some ways can.stache's virtual DOM. It's the piece of technology that, given some object, produces a document fragment and can be used to wire up behaviors on different parts of a document fragment. So we kind of give an object form of the DOM to this can.viewTarget, and it gives us a target object, that hydrate method, that will convert that data to a fragment, and then any functions in this target data will be able to call back those functions on the fragment. So I'll show what that means. So let's say we had a template like this. We have an H1, it's got a class, and it's got hello text, then a some live area, and then a bang. So another text node, and then it closes the H1 element. What we would convert this to, if we're just using can.viewTarget, is this is kind of like our representation, or kind of our virtual DOM-ish like thing. We have you pass can.viewTarget an array of element specifiers, or strings, and essentially each object, which is an element specifier, specifies the tag for the element, any attributes on the element, and then the element's children. And if there's strings, those are just created into text nodes, and if there's functions, a placeholder text node is created there, and then the target hydrate method will be able to call back this function. And then this is another text node. So, whoop, try to move my sharing thing, and it messed up my presentation. Hold on, let's go back to PowerPoint. Can you still see my screen?
Yeah.
Okay, so what hydrate does, so if we are kind of compiling this target data into a target object. And then we can call hydrate on it, and what it will do is it will produce a fragment like we were looking for. So it'll say hello can.js, because what it does is internally it's going to create a document fragment for this, and then know how to go to like a placeholder text node where this can.js will be, and it'll set that placeholder text node's node value to the data's name. So what it's actually keeping internally to do all of this is on target data. When the target's created, there's a clone object, which is the target document fragment. So it made a document fragment that looks like this, where this H1 has 3 text nodes: a hello, a placeholder text node, and a bang text node. And then it compiles path information on which elements it should be doing a callback on. So in this case, it knows on the 0, 1 object, so first look in the fragment, it has an H1, take the first element of a document fragment, which would be the H1, and go to its second child and call back essentially this function. Right? It stores this information so it can quickly find call these functions, create placeholder text nodes. So this is.
I have a question real quick, Justin. I'm sorry, before you continue on. So the object that you have kind of at the top of the slide here, which seems to be like an object representation of DOM nodes, gets converted into our document fragment, and then the path is no longer using that JavaScript object representation of the DOM node. It's using the actual fragment DOM nodes?
These path information is relative to the child nodes of the fragment.
So the JavaScript object representation is no longer being used. It's only used to build that fragment initially.
It's used to build the fragment and the path information.
Gotcha.
And then this hydrate method uses that. It basically clones this fragment and then goes and calls back every callback function on the placeholder text nodes.
Cool. Perfect. Thanks.
So this is what this can view target. This is actually what Stache is building these. So if you ever see like a section, or a Stache template, or a section within a Stache template, it's basically building out can view target objects. For when you have live binding parts, it's making these functions able to set up live binding. Now, this is a huge improvement over Mustache. I don't really want to go into it because this is kind of an old argument, but basically, the way that Stache hooked up things was, instead of having this path information to know where the callbacks were, it would decorate, make a placeholder span element, and then it would search for every element with data view ID on it, and then call back some registered callback somewhere. So it was much more expensive to find the live binding parts than what the new technique can do. So, and the other thing is, it would have to convert all of this. It would always create the string and then always convert it to document fragment. So it would always do an inner HTML to convert it to a document fragment instead of just cloning a document fragment like what happens now. So the performance benefit of just cloning a fragment versus creating a fragment from string every time is pretty dramatic performance difference. So this is part of the reason why Stache is much faster than Mustache. And also not having to walk through every single element that has and see if it has a data view ID property versus just going straight to the nodes is another huge performance benefit of Stache. So those parts make it much quicker. There's some other potential performance benefits that it doesn't do, but basically, well, this might be fun for people who are watching. One thing it could do for minor performance improvement, so right now we have a for loop that kind of goes through the paths, the path information. So we have this path information here, and I basically do a for loop that says, okay, first go to the 0th, then the next iteration loop goes to the second child node, and so forth. One thing I could do to get a moderate performance benefit would be, instead of making a for loop, I could actually inline a function that would have these kind of things hard-coded. So instead of having for loop, you can actually generate a function that will read those properties explicitly, and that has some decent improvements in Firefox, but not really anything in Chrome. But what that would allow you to do is if I could, instead of writing out child node 0, I could write out, I could use first child in those places. And doing child node 0 versus first child is twice as fast in most browsers. So that'd be a slight optimization, but where the live binding parts happen to be the first child of an element, that would be a big performance benefit. So that's can.stache. That's can.target. That's where a lot of the performance benefits of stache come from. Now, the next thing you need to do to be able to create those targets is you need to actually be able to understand the template. You need to be able to parse the template and build up those can.viewTarget objects appropriately. This is where can.viewParser is used, where essentially you pass it a template and you get, as it reaches different parts of that template, it calls back functions with information about those parts. What I mean is, again, if you take this template and you passed it to can.viewParser, here's kind of what it would call back with. So these would all be functions here. And I'm going to explain what, if you put functions here, what those functions get called back with. So first, it's going to find the H1, a starting of an H1 element. So it's going to say, hey, H1 is started. It's going to say false here because this H1 does not self-close. So it says this is an H1, but it's not a self-closed H1, so it's false. Then it's going to say an attribute has started of type class. Then it's going to say an attribute value. We got an attribute value of title. Then we're ending the class attribute definition. And then we're ending the H1 opening tag, basically. When you close the H1, you get close. So this is ending the H1 tag. Then it's going to say, hey, we got some characters. Hello. Then we have a special, which means some magic tag was found. Then some more characters. And then we're going to close the H1 element. And then finally, it's going to say we're done parsing. So done. So I'm going to show, now that we have can.viewTarget and can.viewParser, I can actually build a kind of a microscopic working version of a template engine. And I'm going to kind of show the code for this, but I'll highlight the important parts. Essentially, I'm going to parse the template, and I'm going to keep the target data that I'm eventually going to compile and return a renderer function. I'm going to compile that target data to a target object. I'm going to make the render function and return a renderer function for this template, and it's just going to call target hydrate and pass it whatever data was passed to this render function. So I really am building this target data object is what I need to build. What I'm going to do is, when I find some special live binding stuff, I'm going to add a function to the appropriate place in target data that special is always called with like the expression inside the curly, so maybe name or whatever you're trying to look up. I'm going to say, hey, given the data that someone might have passed to the renderer, I want to look that name property up. I'm going to set that as the placeholder text node's node value. So we can actually look at this happening. Let me know if I need to increase my font size.
Looks good to me.
All right, so here is the working. Let me increase this. Okay, so here is my pseudo stash. You can see at the end here, I'm calling pseudo stash, and that gives me a renderer function. I'm calling renderer with some data, and appending that to the document. And we get hello holler. Let's step through and see what the heck's going on. So my pseudo-stash is creating some target data, and you'll see there's some methods that control where we're at. As we go into elements, we need to have a stack to know exactly where we're adding to target data. What I mean is, if we have an H1, well, when we start, we're adding directly to target data, right? We're adding new elements and objects directly to target data. But once we get inside the H1, we need to add to the children of the H1. And then if we pop out of the H1, if this template continued past the closing tag of the H1, well, then we would need to add directly to target data again. So we kind of need a stack structure to maintain whose children are we adding things to. So I have a stack who's going to maintain what is the current kind of element we're working within, and I have methods that help me get the top of the stack, add something to the, or push a new, essentially, element onto the stack. When we end an element, pop off the stack, and then add children to whatever's on top of the stack. So I have some methods that help coordinate that. And then I'm just going to be, I'm setting up my callbacks. I'll put breakpoints in here for the parsing to manipulate the stack and target data correctly. So let's walk through. So here we're parsing. We got the start of we got the start of the H1 tag. So we're going to push that as like a new element onto the target data and say that, hey, this is our new, we're going to put this at the top of the stack and push this into the target data and say, hey, this is the new element we're working within. And we'll create a target data like object with the tag, no attributes, and no children. And I'm just going to put in my watch up here, target data, so we can see what happens as we do things. So right now it's empty. Now we just added the H1, but it's got no children. Now when we start an attribute like class, we're going to say, hey, well, we're going to get the top of the stack, which is our H1, and we're going to say, hey, there's an attribute. You have an attribute, but we're going to start it off as an empty string, but at least knowing that there is an attribute there. And then we're going to say what is ever our current attribute. So if there's a value, which we'll get to next, if there's a value, well, we know what current attribute we're working on, so we'll use that and we'll add whatever that attribute value is to that attribute. At this point, target data will have the H1 will have a class title attribute. Now we got to the hello. It's going to just add as a child to the current top of the stack the characters. So now our H1 will have a child, hello, and now finally we're getting to the expression, or to the special, which we say, hey, we want to look up the value of name, and essentially set up some live binding there. What this is going to do is add as a child to the H1 this function that, given the data that the template is called with, updates this placeholder text node's node value to whatever this should be, right? To whatever data's expression property is. So I can set a breakpoint in here to see what happens when that gets called. Then finally, we're adding the bang. We're going to pop. And I think we have a breakpoint on what's going to target. So then our final target data looks like we've already seen. We've got 3 children, and we got that function. And when we compile this, the target data, you can see the clone document fragment, and it has this paths information. So it knows to call the 0th basically the first child and then the second child of the document fragment, and then call this callback here. And when we hit play again, we'll actually get into this add function because it was now called, and we'll say, hey, set the node value, which we'll do, and that's how we get hello hollow. So that on a very small scale is how Stache works. Now it's not doing any live binding or any fun scope-like things, and that's what we're going to talk about next.
What was can.k? Did I miss that part?
Can.k is just a function, just an empty function.
Ah, okay.
Other frameworks use that too. It's just like if you just need a placeholder function.
Why is it K?
I don't know, but that's what I think jQuery does, and somebody else does that too. That's a question for Ralph. It's been there forever. Okay. So the next thing, what we want is to, so we made it so that this is just a normal, this is kind of what we have right now is basically a very fast templating engine that doesn't do any live binding, right? We could just clone a fragment very quickly, go right to the places that need to be live and update them. But it would probably actually be fast if the whole thing would, well, I don't know. I don't know how this would compare overall to just like a string-based templating language. The cloning the fragments is much faster. I'd be interested to see. But now let's talk about how to set up live binding. CanView has this other sub-library called CanView Live, and this has a bunch of methods that, given a node and a compute, try to keep some part of the node updated with whatever the value of the compute is. So for instance, CanView Live text will keep a text node updated with whatever the value of this compute is. CanView Live HTML will actually keep this node, but it'll actually replace this node in place with whatever the result of this compute is, if this compute is HTML. This will keep a bunch of attributes live for a node. This will keep a single attribute live, and this is probably the most complex one, which is this assumes this compute is going to be a list. It's going to resolve to a list of elements, or sorry, a list of just a CanView list or an array, really CanView list. And here's a renderer function for each item in that list, and this will keep, as items are added or removed from this list, or the list changes, it will keep the content where this node exists live to the value of this compute plus this renderer. So, for instance, if we wanted to keep that placeholder text node live with this map's name, what I could do is create the document, or create an H1 and add the hello, and then a placeholder text node, and then the bang text node. What I'm going to do is call CanView Live on the placeholder and pass it the compute that is bound to the person's name. And then if the name were to change, this compute would just update that text node. So we're going to add this live binding in can.stache so that if we call it and then change the attribute later, live binding works. So all that I'm doing is from the previous can.stache is I'm just changing it so the function, instead of just looking up on data the expression property, instead it's going to make a compute that will call, it assumes data is a map, it'll just call data.atter with that expression as long as data is a map. And then it will call CanView Live, it'll call CanView Live text with that compute. Right, so we're just changing the way that the text node gets updated use can.viewLiveText.
In this case, the context to this is what again?
This is the text node.
Text node. Okay.
Functions that can.viewTarget calls back, or this is always the text node.
So can.viewLiveText will get the text node that it's going to be maintaining, and then the compute function that will determine when it gets updated.
Yep, exactly right. So this is sudo stash 2.
Justin, one other question. I know that we have this convenience method, can.map.compute, that'll make a compute out of any property. Is there any performance advantage to using that over creating the compute yourself?
Oh, sorry, can you say that again?
Can.map.compute?
No.
No, there's no performance advantage. Gotcha.
So yeah, just to show, I mean, it works if I refresh the page. You can see it says hello Justin, then it says hello live binding, because in the page after second we're changing the name of this map to live binding. And all it has is that same change, which is just making a compute given the data and the expression, and then passing that to can.viewLiveText. I'm not going to go into can.viewLiveText works, because it's actually that's the simplest one. It just binds on this compute for the most part, and when it changes, updates the node value of the text node. It's a little bit more complex only because it knows if the parent has been removed, then it will undo its event bindings. It's a little bit more complex because of memory safety. Next one. Okay, so the next problem. So the problem with what we just made is that it doesn't work great in all, like whatever the data type is. It's really hard coded to just work if the data type is a map, and that's the only place where it'll ever really work with live binding. We want it to. So hey, let's say instead of a can map, I passed it an object with a name property that was a compute. Right? I'd want it to still work in this scenario. So if I update the compute, it still works. So CanJS has a method called can.compute_read, which it's kind of like its own version of the dot operator in some ways for stash, where given an object and some properties, this will read those properties so that they're all observable. And it returns an object that essentially says what was the last parent property, parent object. If you have like foo.bar, it's going to return whatever the foo property of parent is. So it's like what is the most immediate parent if you have to do like kind of set up your proxy binding if you were getting a function back and you wanted that function bound to I'm talking about like function binding. If you wanted that function bound to its parent object, you have it now, and the actual value that's returned. So can.compute_read, its actually API has changed a little bit, but it's never been public, so it doesn't matter. It's very similar. It's just these are objects now that let you know if the operator was called. Essentially, so if I created that same compute, now on parent, I can call can.compute_read and say, hey, I want to read, oh, sorry, this object, I forgot to take a step back. You'll notice the data structure here is I've created a person can map with a name property that has first and an object which has a first property that's Hank. And I put that person in a compute, wrapping in a compute, and then I've got an object that has the compute to this person object. And what I want to be able to do in my template is called person name first. And it would be able to say, oh, person's just a normal property, but then I'm going to read the compute, get the map out of it, and then do .atter name.first on that map. That's what can.compute_read can do. That's why you get result.value is hanged. So all I'm going to change now to make it work with kind of almost any data structure is I'm going to use can.compute_read and then split the expression on the dot operator. And that's how I'm going to build this compute. So that's what sudo stash 3 does. Or it explodes because I must have changed something. Oh boy, what did I change? I checked the first two when I was like, okay, let's make sure everything is working and there's nothing breaking. I checked the first two and I must have done something wrong here. Or maybe it's pointing at a more recent version of can.js. Where's the... No. What's going on? Name. Compute. Why is it thinking it's a function? That's interesting. Name is not a function. It sure should be. Let's see what name is. Oh, that something's weird.
Is that a...
Hmm?
That looked like a string, not a function.
Yeah. I don't know why it would be. The only thing... Oh, there's already a name?
Oh, it looks like it's serving that file from... Oh, never mind. Sorry. Thought maybe that was an alternate workspace version.
What version is... Oh, 2.13. I'm not sure what's going on. I have a feeling like maybe I was messing around with this version of can.js and it broke because I don't know how name exists even, unless it's thinking window.name. I mean, maybe there's a leaky variable somewhere. So I guess I can fix that if I wanted to by doing let's do that. See if that makes its own private version of name. That's better. All right, I think it's working now. I don't know where that leaking name is coming from, but I don't much care for it. Okay, so this works. And again, all I changed is just so can.compute_read is doing the reading of the expression from whatever data was passed in. Okay. Why is this not playing? Okay, so the next problem we're facing is scope lookup. And this is can.stache's ability to look for values in multiple places and have different sections have essentially different contexts. in different scopes. So let's say I have my pseudo-stash and I wanted to pass it this. I want to say, hey, if there's a person, and I want to change the context to the person object within this template, I want to pass it this data. So you'll notice here this map has a greeting property and a person property with a name to stranger. Now I'm changing the context to person, but the data object here is still going to be in the scope. That's why it should still be able to look up greeting. Really, this greeting should try to find greeting on person, not find it, then find greeting on the root context, which is data. Name, when it looks up name, it'll do the same thing, but it'll find name on the current context, which is person, and not have to walk up to the parent context, which is data. So I want something like this to work. This ability to have scopes and look up values and kind of cross multiple contexts is done with can.view_scope. This is kind of like a one-directional linked list implementation, but it really ends up looking more like a tree in a lot of ways. But only you're going. I don't know. I guess it would be you only have access from your your leaves up to the root, and the root cannot go the other way. So to create a new scope. So it's kind of the naming terminology is very weird here, and I'm not actually sure what to call these things, and never have been, and I go back and forth all the time. An instance of scope is really like a context plus a pointer to your parent scope. It's in some ways the nodes in your. If conceptually your scope is all of your context you can look up values in, well, a scope instance really represents a single node you're going to look in, the data you're going to look within, and where you're going to go next to look at data. So you can create scope instances like this. I might say I have my base scope, which is that data of that can map object. And then I could create another scope on top of that where things will look in first by saying, hey, first look inside person, and then you're going to look in the base scope next. So you essentially wire up your scope this way. Creating these linkages between scopes, your base scope and top scope. Now if I were to look in the top scope for greeting, well, it's going to look in person first, but eventually
Sorry, hold on a second there, I'm kind of confused. Wouldn't passing this data to the scope
when passing
look
what?
up first? Wouldn't passing the data in the base scope look up the person anyway? Why do we have to call data
So this is to set up this kind of behavior here. What is the scope of inside this person object? It's going to look up things first on person, then on the data object.
Yeah. But the person is part of the data object. I guess that's what's confusing.
Person is part of the data object, but we want to just write. We don't want to write person.name. Yeah. We just want to write name.
Okay, there we go. Okay, got it.
And so when greeting's read, it's going to go to the parent context to look for that.
Well, first we'll look on person, not find a greeting property, and then look in the parent context. This is very similar to how JavaScript functions work and variable lookup works in JavaScript.
That's actually a good comparison, yeah.
Where it'll keep walking up parent function, basically call objects, until it finds a variable. So yeah, so anyways, I'm creating the scope that's actually used to kind of render this inside this H1 needs to first look on person and then look on data, and it's kind of wired up this way. And we can see we can ask a scope to give us compute for a given property. And this will, if I ask for a compute for the greeting property, it'll look for it on person, not find a greeting property, and then look for it on the root data scope, find it there, and return a compute that's connected to this this can map here, the outer can map. And it'll do the same thing for name, but instead it'll find the name on the person and return a compute that's connected to this name property. So what I'm going to change, this to is all of these functions are going to be passed a scope. We're going to assume the data that is always passed to a renderer function is a scope. That's actually true in can.js. Now you might say, oh, I always pass can.stache a map or an object or something like that. Well, you do, but behind the scenes, before it gets to stash, we're converting that to a scope. So let's look at pseudo-stash for it. And then we're going to use a scope compute method. So let's make sure this works. And whoop. So it's this hello friend. I think that's right. Change. Hello, howdy stranger, hello friend. So let's take a look at this. So here I have my subsection, really, if you think about it, and I'm creating that scope lookup so that it looks first on person, then on the data, and I'm passing it that scope to the renderer function. And that renderer function is just using scope compute, which is internally using can compute read to look up the value in the right place and create a compute out of it. So one thing you might be like, well, how do we make the let me open that up. This might be too small, so let me open that up with Sublime maybe. Let me just copy this. All right. Sublime's opening features up. Okay, so you might be wondering, like, well, hey, Justin, this is lame. I want to see how that actually works if you have like person and person here, right? Like, you're not showing us the full thing. Well, first I'll say too bad because it would take forever to walk through how all of this works. Although you can imagine it pretty easy. What is actually happening is when Stash sees a new subsection like this, it's saying, hey, there's a new section starting. It actually builds this into its own sub-template. There's actually a can view target. There's actually a stack. Like we have a stack of elements for a given target data, there's actually a stack of target datas itself. So when we encounter a new subsection, we actually create a new target data object that we're adding things to. And we set up that target data so it takes the old outer scope. We set up that renderer function that we're creating here, kind of like we're creating here, and we set it up so it's taking that old outer scope and making any adjustments to it before it calls the hydrate method on the inner target data output, basically. I don't know if that made sense, but basically, like, we treat this as almost like a mini template itself. And the outside, on the way to actually calling this, we're doing these kind of scope adjustments based on what's going on in here. But it's beyond the scope of this talk to really get into that.
Was that a scope joke?
No pun intended. I have no sense of humor when it comes to software. Zero. I'm just ones and zeros, baby. All right. Okay, so then the final and probably worst part of making live binding work is node lists. And I think, David, you had a recent encounter with these fun parts of Dun.js, or
All the time.
Huh?
All the time.
All the time. Okay, so the problem comes from if you want live binding syntax like we have up here, where there's a nested structure, but not necessarily a nested DOM, meaning I have this live section where, hey, if there's a person, I want to render this like, and then I have hobbies within that. So if person is suddenly removed, I need to somehow tell hobbies like, hey, stop doing live binding and remove yourself. And if owner, stop doing live binding and remove yourself. There's no DOM hierarchy between these things. These are all just like all child nodes. Hobbies, like, the person is all just a child node of the div, which makes things really tricky. So we have to kind of maintain our own hierarchy of the text nodes within a div. So this is what node lists do, and we're going to talk about that. So you can think about it if we had a template like this and we rendered it with this data here. We have a can map, it's got a person, and it has hobbies, and it's on our true. That would produce text nodes within the div. It would produce, within the div, these would be the elements of the text node. There would be an I followed by a line break. And then a line break after this person with like, and then a line break. And then each hobby would produce a span. In reality, actually, there's another text node here, but I'm going to ignore that for now. And the dot here, and a line break, and then the label, and then a line break before person. So what we need to do is create that hierarchy where essentially like these spans and the label really belong inside the person live binding. So when we're rendering the live binding here, and you remember there's a callback here, right? All we do at first is we say, hey, there's a I text node, and then there's a text node, there's a placeholder text node for person. And we're going to call a function back on that, and then we're going to call the subsection renderers after that. So what this person function, so first we'll render I, then the placeholder text node. Then the placeholder text node is going to be called and replace itself with the like, a placeholder text node for the each, a line break here, and a placeholder text node for the if, and then another line break here. Then the each function is going to be called back, each placeholder, and that might change those to spans. And then the if is going to be called back, and that's going to change it to a label. So that's kind of how things are called back, and they're always replacing their child text nodes. What we need to do is, hey, let's say if person was removed, if person became falsy, we need to take all of these elements here and remove them. So, and tear down all the live binding that's set up inside those elements. So what we do is when person is about to be rendered, it says, I'm going to create a list of nodes so that I just rendered out. So each is the placeholder text node for each is in there, the placeholder text node for if is in there, and all of the other text nodes around it. So this person knows, hey, this is the stuff that's like inside me, the elements inside me. Then when each runs, it knows about its parent placeholder, and it'll find its position within that parent placeholder and say, oh, well, instead of this placeholder text node, I'm going to replace the placeholder text node in this array with a pointer to my node list, these spans. And if is going to do the same thing. So really what you have is a list of lists. So you have a list where there's going to either be text nodes or other DOM elements or other node lists. So these are node lists. So what happens though is, let's say we added to hobbies. Well then this live binding for hobbies, well, it can be smart enough to add to its own list of text nodes, which it does. Okay, cool. That works. Now this is really nice because then if person is ever removed, well, all it has to do is recursively remove this element. Then, hey, I'm going to recursively, if I'm looking at if I'm looking at another node list, I go to that node list and recursively remove any elements or other node lists in this node list. Right? So this way, when person is removed, we can go tear down all of the live bindings which are associated with the node lists and remove all of the elements if like person is removed. So those are node lists. They're APIs. Basically, you register your array of node lists, and you can update your array of node lists with new nodes. And you have a teardown when you first register. This is like so you can unbind yourself. If anything, if your parent is unbound or you need to unbind yourself, this teardown will be called. And you can unregister when it's actually, you need to tear down yourself. You can unregister yourself. So with the previous example in mind, how this could all be wired up is something like this. You have there's this helper, by the way, in can.stache where you can actually pass a fragment like this, and it'll create placeholder text nodes, which is really nice. So that would create 1, 2, 3, 4, 5 text nodes, and the empty ones we're saying are placeholders. So this is what person looks like. I could say, hey, I want to register. These are person's nodes that it cares about. Then I'm going to say, hey, each is going to register the node that it cares about, which is this first placeholder text node. So it has its own array of the first, there's just this one element in it. And then each is going to say, here's what elements I'm actually going to. I'm going to these spans. And then I'm going to say, my original text node, my original nodes, which is this placeholder text node, I don't want that anymore. Instead, I want these elements, these child nodes that we just created. And we can do the same thing with if and say, okay, on this element, you're going to register. The good thing about this is this 3 stays the same position, which you might notice. It's like, well, we were just adding 2 spans, but because this text node is being replaced by a pointer to this list, this 3 can still say the same number. It doesn't have to shift by 2. And so we register, we would create the elements that the if wants to create. Then we say, well, instead of pointing at this text node here, point at these child nodes. So eventually person list ends up looking like this, where you have an array, but you've got your placeholder text node, but then you have a pointer to the array that's registered here, but it actually has these child nodes in it, and the array here, but instead of having this, it's got the child nodes of the if in it. And that is...
So, real quick question. Does that mean that person list is a target data? That's the target data of node list? I'm sorry, person list? Because that looks like that little comment representation of the value looks like the target data that we were generating earlier with can.view_target.
None of this is target data. These are all elements.
Okay. I was thrown off a little bit by the pipes.
Oh, that's just me trying to represent a text node.
Okay. Got it.
I guess this should have looked with pipes as well. I don't know why. Actually, I was being inconsistent, actually. I should have been pipes here as well, because this would have been not a string. Think this. It's basically a weird way of maintaining hierarchy when there is no hierarchy. You're just, it's just, these are all just children of the div, but we need to maintain a hierarchy within that to say, like, well, the person is kind of the parent of these spans and this label and this other kind of live area.
So it's mapping the contexts, the parent contexts, to the node tree, right? So we have like a tree of context.
I would say it's mapping the live binding sections to the node to the nodes in the DOM.
Right. Cool.
So that's it. I mean, that if you understand all of those are the big parts of can.stache. Everything else is like, if you understand those fundamentally, you can kind of start going through can.stache code and actually like have some feeling for what's going on. Hopefully, maybe debug a little bit if there's bugs or problems and make fixes. There's still a lot you'd have to learn on top of that, but it is those are the basics of how everything pieces together. So that is it. That's my presentation.
Very cool. Thank you.
Yeah, that's what it takes to build just a small piece of what it takes to build a live binding template engine.
Right on.
Well, thanks for joining, guys. I don't know what next week is. Maybe it's can fixture, can connect, something like that. Hope to see you then.
All right. Have a good one, guys.